The word of prayer. Dear Father, we thank you for this day again. I thank you for this class and these students. Ask you to guide our steps today. Help us to prepare for the test tomorrow and to glorify you in what we do, Lord. In my prayer, Lord Jesus. Amen. Well, eventually, yes, we have a visitor. I should warn you, he's armed. Uh-oh. So there you go, 0918. Let me get straight to the, let's see here. All right, was there anything wrong in this one? Or did I do this one correct? I have a bunch of errors in this surprise attack mission solutions. I'm trying to remember where. I think it might have been 9. Maybe this one's okay. I think this one was okay. Yeah, this one was okay. All right, this one I had. Let's see here if we can find the errors.
Hello.
Hello. All right, so this one here, basically we kind of reverse engineer the bounds to see that it's part of a sphere, right? Part of a ball in the first octant, apparently. And I think this one's okay, right? Yeah, this one's okay. This one, on the other hand, I messed up because I have not paid attention to the details of my own problem. So you guys, several of you have pointed this out to me in email, which I appreciate. That is totally bogus because this means row squared is between a 1 and 4, right? So rows should go from 1 to 2. The 2 is okay, but the 0, no. So that should be like 2 to the 5th minus 1 to the 5th divided by 5, right? Which is 31. So that's supposed to be a 31, and as a consequence, this should be a 62 pi over 15. All right, so there's that. And some of you guys told me about that last class, but I just didn't process what you told me. Was that the mistake? Was there another mistake? That was it? There was something else that you guys told me about in the email. I can't remember where it was. Where was it? Can you guys remind me? Was it the mission or?
Yeah, it was in the end of chapter.
Oh, the end of chapter problems. Oh, that's. Oh goodness, that's going to take me a minute to find that. Come on. End of chapter problems. 56, you say? Let's see here. Oh, 156. Oh, yeah. That'd probably make more sense, wouldn't it? Let's see here. So the 156 was.
The initial area should be 1, right?
Oh, yes. Yeah, somebody told me about this a couple days ago, and I just haven't gotten a chance to communicate to everybody. But yeah, that area should not be 2, because it goes from 1 to 3 and from. Wait a minute. Yeah, 1 to 2 and 3 to 4. I'm sorry, I was whatever mistake I made before, I made again. But anyway, yes, 1 to 2 and 3 to 4. So we're going 1 unit in x and 1 unit in y. So the delta x, delta y is just 1. So yeah, so this should be 21 over 4. Was there anything else in the end of chapter problems that needed comment? You already give them a ticket. Oh my goodness. All right. Do they have it coming? let's see here. So, I think in terms of the math battle, I hope you all have, taken some time to work out the problems for yourself. I know there's not enough time to do all of them, for everybody to do all of them during the class time, right? But hopefully you studied them. This one, if this was a test question, goodness gracious, I hope all of you would get it, Like, this is a gift, right? So, that one's not bad. Problem 2 is, it's kind of the heavy-handed way of asking you to change the bounds, right? Because you can't do the integral to start with. So the only choice you have is to reformulate the integral instead of a type 1 as a type 2, right? And so the type 2 description, we go from 0 to x over 3, and y goes from 0 to 6. And so with that adjustment, then we can calculate that. So I think the class got that right too. This problem brought to you courtesy of ChatGPT. It's pretty good for making up problems that have stupid answers. But whoa. Was that for me? Oh, okay. Don't shoot the students unless they have it coming. And even then, not in the eyes. Okay, all right. So any questions about this one? I mean, basically you need to set up, there's two options, right? You could either go type 1 or type 2 here, but I prefer type 1 if I can do, so I set it up as a type 1 type integration, and then we just have to do the integrals, which work out like you might expect. Problem 4, this here is, there's a sphere and a cone, right? But the cone, so, I've done this in a few different places, like change z to sphericals, change r to sphericals, work out the tangent. It might be worth knowing how the tangent of phi is related to, to z and r, just as like a kind of a checkpoint for things that you know. I think I'll do that in the next problem solution, but anyway. I don't really have much to say about these. Oh, look, all right. So, yeah, this next one is kind of the same sort of thing. Not exactly, because this one's a paraboloid that opens up at 1, and then you've got, a flat top. So that's the volume. Cylindrical coordinates is a nice setup here. Theta goes full sweep. R goes from 0 to 2. And then to refine that, like if I just did this alone, that gives you an infinite circular cylinder of radius 2, right? But then to carve that down further, z goes between this and that. And you got to put your bounds in terms of cylindrical coordinates if you're going to use a cylindrical setup, but that is one way to do it. And so that worked out like that. This one here, whoa, okay. So here, this one's a little bit more challenging, I think, but everyone should study this one. Make sure you really understand this one. There's lots of different ways of asking this kind of question, but this is what I was just talking about. It probably would be smart to notice that the tangent of phi is r over z. This is, that's a useful formula to know. It kind of saves you a bunch of work when you use it. And so that helps me sort of decode the angle of the cone in question here, which happens to be inverse tangent of 1/2, which is, like I say, nothing special. But then looking at this kind of half of a cone, you can see that the x goes from -9 to 9. You can see that y is bounded basically by this green curve up here, which, so if I just had this and that would give me an infinite half cylinder, right? But then to carve that down further, I make z go between 18 and the bottom here, which is the red part, the cone. And so there's the setup for the, yep.
So what's solving like integral problems on the test tomorrow
Yes, you do need to be able to draw out the regions, because otherwise I don't think you can really understand the problems, yeah. It's definitely part of what we're doing. What's that? Yes, you need to know how to draw all of them. Yeah, yeah. But, I mean, there are strategies, right? So, you know, if you want to see what the thing looks like, you can specialize, put x equals to 0 to find out what it looks like on the YZ plane, put y equals to 0 to see what it looks like on the XZ plane, things like this, Looking at z equal to a constant, what kind of slice do you get for the surface? You can specialize, like fix the values of the Cartesian variables to learn information about like what is the surface you're looking at look like in those particular contexts. But yes, we've had a bunch of examples, and I do want you guys to learn from the examples I've shown you and like meditate on the patterns that we've seen, and so all of those are examples that I draw from. And certainly you should be ready for like the standard shapes that come with the coordinate systems, right? Like cones and half planes and spheres come with spherical coordinates, right? That's dangerous, man. You poke somebody in the eye. What are you doing? Yeah, that's right. Do you guys know about what you talk about, Willis? Whoa, I thought that was forgotten. That's a deep cut. Wow. Man, I don't remember anything from that show except that. That's like all I remember from that. And also my mom wouldn't let me watch it, but let's see here. So that's how old that is. But my mom wouldn't let me watch it. Consider those words from me. But so what I was going to say is, there's common shapes that are sort of characteristic of all the different coordinate systems, like cones and spheres and half planes for spherical coordinates. For cylindrical coordinates, again, you get half planes. Horizontal planes for z, right? And cylinders, right, for r equals to a constant. And then, of course, for Cartesian coordinates, well, we just kind of take it for granted, fixing the planes. But yeah, you do need to be able to draw things. I can't give you a picture-free treatment of Calculus 3. It just doesn't exist, yeah. At least I haven't taught it anyway. So in cylindrical coordinates, we go from 0 to pi, from 0 to 9. And the z bounds we can reformulate in cylindrical coordinates like that. So that's what we get there. There are other, this is not the only choice, right? You could easily flip-flop these two, wouldn't change a thing, right? Except that you probably also must flip these as well. Somewhere somebody sent me a comment, an email about having the r and the z bounds flipped in a calculation. Where was that? All right, well, I'll make an announcement after the class then, because there's something else I have not corrected yet in my solutions. I don't think it's in this, though. I think it was in anyway, we'll get back to it. If I don't find it today, we'll talk about it. I'll make an announcement later. But and then for spherical coordinates, it's kind of the most adventurous one because, annoyingly, so the other thing is integrand, right? For the cylindricals, I have to trade x for r cosine theta, and z is z. But for sphericals, x is rho cosine theta sine phi, and z is rho cosine phi. So that's exciting. And the dv is rho squared sine phi d rho d phi d theta here. And we figured out the angle up top when I was doing my initial kind of survey of what I was looking at. The theta goes from 0 to pi because we're sweeping out where y is positive. This is not as obvious, but this is coming from the fact that the cone, the equation for the top, right? Actually, not the cone, but the top is equals to 18 is rho cosine phi. So if I solve that for rho, I get 18 over cosine phi. So that's the equation for the top. It's also why you'd really rather not come up against the need to do this integral in spherical coordinates because, I don't know, 1 over cosine phi it's not a happy place. But then again, I would probably engineer it so somehow or another the integral didn't work out that bad. Problem. He worked ahead in his school last week so he could come here. I mean, he's been looking forward to this.
Cool kid, okay?
Yeah, exactly. Away from his brothers and with you guys. This is living. Uh-oh. Any questions about this? So these kinds of problems, you really just have to graph carefully and, come to an understanding. Now this one here, I kind of pigeonholed you into this substitution, so once you have that given, then there's different ways to go about here. The other way to do this would have just been to pick the 4 points that are the 4 corners here, doot, 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 and doot, and just map where those go to, and then connect the dots. Like, you could have done that. If you do that, you can also do that. Like, I found it convenient here to look at the Cartesian equations and just translate them into x minus y is equal to 3, but this was given to be v, so we got v equals to 3. This is v equals to 4. This one we can translate into 2x plus y equals to 0. So, but the 2x plus y is also u, so u is equal to 0 is the red. And the green is x equal to 0. Now x equal to 0, I had to use both of them to get this one. X equal to 0 specializes u equals to 2x plus y to just u equal to y, and v equal to x minus y to v is equal to 0 minus y, which is v equal to minus y. And then I was able to put those together to get that v was minus u, because I don't want y in the formulation for the uv equation, right? I need to eliminate y. That's kind of what's going on there. Anyway, after the dust settles, you've got a region in the uv plane, and I use this trick to calculate the Jacobian of the inverse transformation, basically, is minus a third. And then that flip-flops for this one to the absolute value of 1/3 in the change of variables theorem, which then gives me this. And again, cool stuff happens in terms of once you do the integration, the inside integration, then you can do a substitution to do the integral. And anyway, you guys got this one, so yes, sir.
I'm like just not looking over it like now, but what are you like trying to find like here? I was confused.
Oh, what's the problem? The problem is to calculate this integral over the region R, which is given, R is described by the being bounded by 4 lines, so you have to kind of understand what R looks like. And then, because you cannot do the integral of e to the x minus y squared, you have to do something. And it turns out that if you make this substitution, it works out nicely. But if you just tried to do it directly in the Cartesian coordinates, it wouldn't go well for you, I don't think. I mean, maybe it would. I haven't tried, but yeah. So this is a combination of you have to use the right type, like type 1 or type 2 kind of problem, combined with the substitution theorem. This one here was this one wasn't what I wanted. So I just gave you guys full credit for it, but if you did something wrong, I wouldn't have noticed. And I definitely did something wrong. It was pointed out to me that I have the 6 here like it belongs, but then that vanishes here. Oops. And that matters because that 6 multiplies this 1, so I should have, this should have ended up being 24 pi over 3, or 8 pi actually, because this 6 should multiply this as well. Ooh. Oh, man. Yowzers. So what I was aiming for, what I was trying to do, guys, is I wanted it to work out so that this was like an odd function over the integration region. And so that piece just integrated to 0. And I don't think it quite did. So if it did, I don't see it yet. And I definitely don't want to do this integral. So, and this is also a mistake because it was supposed to be x. Is this x plus 1? No. I'm supposed to have rho sine phi cosine theta, right? So I'm missing a sine phi here. I think this one's okay. This is the z, w plus 1, which is, I'm using w is equal to rho cosine phi, so rho cosine phi plus 1 makes sense here. But the u plus 1 should be rho cosine phi sine there's a sine phi missing here. Again, it's kind of irrelevant because I didn't actually work it out, but But I was trying to make part of the math battle that seeing that you picked up on the integral of an odd function is 0, you know, because we've done a lot of that in class, and I thought it should be reflected in the math battle, and I failed. So there's really only one other place I have to fix that, you know, just saying. I would expect that there's some place on the test where you ought to use the odd function theorem. Integral of an odd function about a symmetric interval of the origin 0. This one, I think this is a friendly problem. This is just a usual, like a nice polar area because it's bounded clearly between two angles, pi over 3 and pi over 4, and the radius goes from 0 to apparently 3. And so, yeah, we just got to remember dA is r d theta. That's the polar Jacobian, and there it is, yeah. Friendly reminder, you do need a calculator for the test tomorrow. Like I had 2 or 3 of you last test not have a calculator, which is kind of a big deal in here. Like bringing a calculator is part of the test, and I will take off points if you don't have it, because you won't be able to do certain things. And I do grade, not a lot, but I do grade some on your ability to punch numbers into a calculator and do it successfully. Okay, so anyway, that comment. If you don't have a calculator, you can of course borrow one from the math department usually, unless Miss Guthrie's not there when you need to go get it, which means that you're playing a dangerous game. But all right, anyway, enough about that. Let's see here. Here, this is just find the mass of B, so the density was given. Integrate the density over volume. This problem should scream at you, use spherical coordinates, right? Because it's like, it's a ball, that's a spherical bound. The density's it's 1 over 1 plus rho squared. Like that's very, very spherical, so use spherical coordinates. And yeah, things work out nicely. I mean, the integration does require a little bit of finagling, but I just add 0, plus 1, minus 1. That brings me to a 1 minus that. If you don't know that, you could do long division, for example, to get from here to here. Whatever, but you got to see something to get from here to here, otherwise you can't do that integral. And that is a standard Calc 2 integral that you should know how to do, especially now that it's appeared on work that I've given you. Yeah, so. And then this problem. Yeah, I don't think you guys really quite got it. I mean, the part A, pretty close to getting it. Part A, very close, reasonably close. Part B, no. I don't think it happened. Like we did this much in class, right? We did this and that in class. Now I didn't use the same notation, right? I used R and I used rho, right? And I used phi instead of phi3. But actually the last problem in the homework was this. The last problem in the homework was already the n equals 4 case. It's just I used a different, I forget what I used for the radius, but I had like psi. We had sine squared psi and sine phi. All that. So like this actually was in the last problem in the homework, which you guys did, but that was not reflected in the answer that was given to me. And so it's worse than you thought. It ends up being like this is the general pattern. It's like the n minus second power of sine all the way down to sine squared of phi 4 or sine of phi 3, and so yeah. That's what happened. And there's a full inductive proof. This is not on the test. Relax, right? And then, of course, well, you probably knew what the answer was, but it's some of my finest work. Again, courtesy of ChatGPT. Thank you, ChatGPT. But because if not for ChatGPT, I would have messed this up, I'm sure. But yeah. Actually, I didn't just do ChatGPT because it can't be trusted. I like Googled something and ChatGPT'd, and it agreed. I was like, okay. We're good. So, ethical use of AI to antagonize students, right? Any questions about anything? Let me stop talking. So we just have one mission, right? And the problems that we've gone over in class. So is there anything in here that kind of stands out at you? I mean, I messed up. Well, I didn't mess it up. I mean, I fixed it before I got messed up, but problem 85, the original solution I had, was bogus because I talked myself into this being the region which is bounded, which is just nonsense. Like, that's not the region between the two circles, right? The region between the two circles, we all agree, like Venn diagrams, right? The middle. So it basically asks to find the centroid of the Venn diagram here. And now some of you pointed out to me it has to be 1, 0. Like, that's just geometrically clear. If you just look at the average of the circles, that's where that happens. So that has to be the centroid. True, right? But we should be able to work it out. And working it out does hurt a little bit. And the critical thing to notice is that if you use the polar coordinates here, there's actually 3 sectors. See, because there's not a well-defined inner and outer radius in that intersection region, right? You got to go. It turns out, so this is like pi over 2 to pi over 3. That's one case. Pi over 3 down here to minus pi over 3 is another case. And then minus pi over 3 to minus pi over 2 is yet another case. Now, there's... Sorry, I don't know what's going on here.
That's your warning.
You've been warned, I guess. So anyway, this took me a minute to work out, but the cool thing is that it does work out like you guys told me to 1. So now over here, I have this. This is not the solution, right? Because I have assumed it's the. That's just nonsense. To keep things nice, assume it's the rightmost region. Like, no, I can't do that. That's just not the question that's asked. But if you did, that would be a different question, right? Find the centroid of the region that's outside of the circle centered at the radius, circle of radius 2 centered at the origin, and inside the circle defined by r equals to 4 cosine theta. If you did that, if that was the problem statement, then this would be the calculation to find the centroid of that thing. What is this thing called? It's got a name. Crescent moon? All right, I'll take it. Now, is this one nicer? Like, is there a well-defined inside radius and outside radius, or does this also do that fragmenting thing? I think it's got a nice. Yeah, if we sweep, like, there's always a well-defined. The inside radius is always given by 2, and the outside radius is always given by the 4 cosine theta. So that's a much friendlier test question than the previous one that I actually asked for your homework, right? So that I mean, I think that's worth. Sorry for the ambiguity here. No, there was no ambiguity. I just read it wrong. I'm sometimes dumb. Usually dumb. Let's see here. Anyway. See, this problem here at the end was part of the math battle. Like, that was problem 11, like, part of it. Early stage. So you could have... Now, I think I've shown a better way to calculate this with the wedge product this semester, but, that's not required content in here. I might ask a bonus question on it, but, like, it wouldn't be a lot, right? So you should definitely focus the lion's share of your effort on being sure you know how to do type 1, type 2 integrals and set up, integrals over cylindricals or sphericals and all that. What are you up to, Benjamin? You're up to something. You're up to something. People are looking at their phone?
Yes.
No. They would not do that while I was talking. That's crazy. No one would do that.
It's the one behind Jacob.
My favorite instance of this once is I had this kid, and he came to my office hours and he basically asked me, like, he's my physics class at the time. He asked me this question. He's like, "Can you explain to me, like, conservation of energy?" And I'm like, I just spent, like, the whole previous lecture, like, deriving that, right? Like, the whole time. You were in class, like, I think you're distracted with the text on your phone or something. You shouldn't be asking me to give you the lecture again in office hours. You were in class, like be in class, right? And he said to me, he said, no, I wasn't texting. I was watching soccer on my phone. I'm like, that's not better. He asked me for a letter of recommendation later. And I told him, I was like, well, I'll write you the letter, but I'm going to talk about the soccer in your letter. He's like, no, you wouldn't. I was like, I will. I am honor bound to talk about that. He still wanted the letter, but whatever. It was for tutoring here. It wasn't anything too serious, but anyway. Any questions? So like the focus of this test is pretty narrow, right? It's just integration. Obviously, you still need to know partial differentiation because you have to do partial differentiation in reverse to do these integrations, half of them. And I guess if I was very creative, I might find a way to work test 2 into test 3, but I haven't come up with anything yet. Any ideas? So, all right, well, with the time we have left, let me know what you don't know so I know how to make the test.
I know everything.
You know everything?
Yep.
So I should put everything on the test is what I'm hearing.
No.
Okay. No? Yeah?
Like power series stuff on it?
Will there be power series stuff on it? Probably not. Yeah. I'll circle back to power series on the final. You got a little bit of time for that. Yeah.
So is this stuff like you feel like explain now? Is that the question? Or not?
I mean, if you tell me what you don't know, then I know what to put on the test, right?
I just kind of figure out how to do like the Jacobian with like 3 or 4 like.
The Jacobian with like 3 or 4 things?
Yeah.
Just calculate the Jacobian? That's the thing you've forgotten?
Yeah.
Ah, good choice. I like it. Don't put that on there. I usually do ask questions like that. It's kind of funny I didn't ask it on the math battle, honestly. Like if we went back and took a look at an old test 3 somewhere, if I could find one. I don't know. What year do you guys want?
2015.
2015? This year? I don't have this year. What do you guys think? Yeah, you guys do not understand the how far behind I am at the moment. I've certainly not written your test yet. Good grief, guys.
We're moving the test to Thursday.
No. That would make more work for me in the big scheme of things. We're definitely keeping the test tomorrow. Although the grader is still working on your mission. That should be available tomorrow morning if you want to get it. But I think you probably already know what you did right or wrong on the basis of the fact solutions posted and all that. But if you do want your graded mission back, I'll leave them outside my office or on a chair in my office so you can find them there. If that's okay with you. Is that okay with you guys? I mean, I'll probably be in my office, but I might wander. But they should hopefully be there by about 9:30. I'll try to make an announcement once I actually have them. Anyway, so here, first order of business. So this is just, this is what is known as a gift, right? This one here, change the order of the bounds on the integral below. So you got a graph and come to understand what the graph looks like, right? So graphing's an issue, yeah. So changing to type 2 gives me that. Notice that I'm not even giving you the formula here, so all you can do is set up. The whole problem is set up, yeah. Next one here, find the volume in the first octant bounded by that plane and the coordinate planes. Oh, and y equals to 1, that's interesting. So I sliced it off at y equals to 1 like that. Chop, chop. And so yeah, we set that up. 6, 7. Sorry, these things will pass. Oh, so disclaimer, this is back with the organization that test 3 is power series and integration. Wouldn't that be fun? So, yeah.
Is this in a module? That's how it works.
Is what?
Where we go to find the
This test? I have not posted this. I'm showing it to you now.
Oh, could you? Or email?
I'm showing it to you now.
Oh, I mean, like, I want to, like, do it, like, on my own.
On your own. You want me to copy? You want me to post a blank copy of it so you can try it?
Yeah.
Yeah, I could do that.
Or you can do the small copy, and I can just try it. Just so I know what the answers are as well.
Well, yeah, I'll post the blank copy and the solution for you guys. Sure. I'll try to do that after class if this guy doesn't distract me. You can see that the battle is real. Oh, hey, I think that problem's familiar. We just worked that. Well, okay, it's not quite. Look at that. So this is a kind of stupid way to tell you, hey, the angle's pi over 7. If you understand what's going on there, that's the slope. Is the tangent of the angle. And here's one of these handy-dandy change of variables problems. This one is a diamond. I gave you the vertices. Ooh. Well, that was uncalled for. What's wrong with me? Why am I telling students that? They should know that. Seriously? Shame on me. Shame on me. But anyway, so that diamond becomes a square, and all right, there's that. What?
In the ones where we have to change it to U and V, will you give us like an equation set up where U and V are both like equal to X?
I make no guarantees. Sometimes you have to invent it for yourself, yeah.
How would we do that if we had to invent it for ourselves?
I guess you have to think. But I mean, I don't have an algorithm. I mean, I kind of look at it and try something, and I mean, if it doesn't, I mean, the whole point is to make the bounds go from something crooked to something rectangular. So if your substitution doesn't make the bounds better, maybe it's not a good deal. I mean, I guess if I was really, really clever, I could come up with one where changing the bounds makes the integral doable. We kind of saw that with like the e to the x minus y parentheses squared problem, which I hid behind the algebra x squared minus 2xy plus y squared. Haha. See, that was very tricky of me. But this is a 2, yeah, okay. Golly, we almost looked at this in the math battle. Almost, but here I actually... All right, let's see here. Anything else? Find the volume bounded by y squared plus z squared equals to 1 and the ellipsoid. Ooh. 2x squared plus y squared plus z squared equal to 3. So it's kind of like carving a cylinder out of a watermelon, kind of, sort of. Anyway, there's that one. Oh, I gave 2 different approaches. You can look at them if you want. Ooh, ninja. We haven't had any. I got to find some ways to bring some ninjas back. Maybe I have to do some test 2 stuff to bring ninja back. No. Not the face, yeah. Anyway, so that's pretty much it. I'll let you guys, so we can stop here for now. If you guys got questions, you can ask them. I'll try to go post this right this moment.